explainer. Today, we're cracking open the tiny, invisible engines that run our entire world, microprocessors. Yeah, they're in your phone, your car, pretty much everything with a plug or a battery. But have you ever stopped to wonder how these little chips got so unbelievably powerful?
Take a look at this. You might just see a bunch of intricate lines, but you're actually looking at the blueprint for the modern world. This is a microprocessor, a single piece of technology that has totally revolutionized almost every part of our lives.
So, what is it really? We call it the brain inside our devices, but what's actually going on inside that miniature metropolis? Okay, let's dive in and take a closer look.
To really get what a chip does, we first need to understand the basic layout of any computer, no matter how big or small it is.
You know, the fundamental concept is actually pretty simple. Just think of it like a digital office. You've got information coming in, that's your input. You store it somewhere, like a filing cabinet. You process it, that's the actual work being done, and then you send the results out.
The real star of the show, though, is the central processing unit, or CPU. That's the brain of the operation. It's got a control unit that acts like a traffic cop, directing everything, and an ALU, the arithmetic and logical unit that does all the heavy lifting, all the math and logic. This is where all the thinking happens. So you've got this brain, but how does it talk to the rest of the computer? Well, it uses something called buses. You can think of these as the computer's nervous system. They're these electronic pathways that connect the CPU to everything else, letting it send and receive data and control the whole system.
And here is the absolute key, the game-changing idea. A microprocessor takes that entire CPU, the traffic cop, the math genius, all of it, and shrinks it down onto one single tiny piece of silicon. That was the breakthrough that changed everything.
But how on earth did we get from computers the size of a room to something you can literally balance on your fingertip? Well, let's take a look at this incredible journey of miniaturization.
You know, back in the 1940s, computers like the famous ENIAC were absolute monsters. We're talking about machines that filled entire rooms with over 17,000 unreliable vacuum tubes that were constantly burning out. They were huge, power-hungry, and needed a ton of upkeep.
The solution was the integrated circuit. This was the magic bullet that allowed engineers to replace those bulky vacuum tubes with tiny little switches called transistors. And then they just started packing more and more and more of them onto a single chip. We went from small-scale integration with just a handful of transistors all the way up to VLSI, very large-scale integration, with literally billions. The leap is just staggering.
And this timeline of early Intel processors just shows you how explosive that growth really was. In 1971, the very first microprocessor had about 2,300 transistors. Now, look at that jump by the year 2000. The Pentium 4 had 43 million. The pace of that change is, well, it's pretty hard to wrap your head around.
Let me put it another way. That's an 18,000-fold increase in the number of transistors in less than 30 years. It's just an absolutely amazing feat of engineering.
Okay, so as these chips got more and more powerful, designers came to a fork in the road. They had to ask a really important question. How should this processor think? What kind of instructions should it be designed to understand?
And this led to two main design philosophies. On one side, you've got RISC, which stands for Reduced Instruction Set Computing. The idea there is to use a small number of really simple, really fast instructions. On the other side, you've got CISC, or Complex Instruction Set Computing, which uses more powerful, complex instructions that can do multiple steps all at once.
A great way to think about it is like this. CISC is like a Swiss Army knife. It's versatile, it can do a lot with one tool, but maybe it's a bit clunky for some jobs. RISC, on the other hand, is like a specialized toolbox. Each tool does one thing perfectly and incredibly fast. And this fundamental design choice, it affects everything from how long your phone's battery lasts to how fast your laptop performs.
So let's tie all of this together. Where has this incredible journey of shrinking technology and clever design actually taken us?
When you boil it all down, the story of the microprocessor is a story of relentless miniaturization and just an explosive growth in power. We went from room-sized machines with a few thousand parts to billions of transistors on a chip smaller than your thumbnail.
And why does this matter so much? Because this isn't just an engineering marvel. It is the fundamental technology that has defined the last 50 years of human progress.
Without the microprocessor, there'd be no personal computers, no internet, no smartphones. It powers our entire digital world, and it's still what's driving the next wave of innovation in fields like AI. And you know what? The journey is far from over. Not even close. Which leaves us all with one final fascinating question to think about. As we keep packing more and more power onto these tiny chips, what problems will a trillion transistor brain solve next? The